Hello everybody, welcome to another math teaching video with Mr. Scarano. In today's video we're going to be talking about the derivatives of inverse functions. So let's get started. Derivatives of inverse functions. Okay, so when we think back to our understanding of inverse functions, which most likely came from our pre-calculus coursework, let's start with a graphical approach of what an inverse function is. Okay, and so let's say I have some regular old function. I'll make some tick marks here. Let's call this function f of x. That's my function f of x. And let's say I have the point here. Let's call this 5, 9. Here's the other side. 5, 9. I'll call this f of x. Okay. The inverse function is graphically, or at least visually, the function that I get if I flip this over the line y equals x. So here's the line y equals x. Okay. And if I flip this over this line, I get the inverse function. So I'll draw that up here. Looks vaguely like that. Round it off a little bit, like that. Okay. So that's the inverse function, f inverse of x. Okay, and so if I'm going to write down a list of a few things that we should know about inverse functions. Here's what we know about inverse functions, and we'll keep this list handy. What do we know? Well, what we've seen so far is that it reflects about the line y equals x. Okay, the inverse function is a reflection about the line y equals x. We also know that if this point 5, 9 exists, then a different point exists on the inverse, and it's pretty straightforward. It's 9, 5. Okay. So if 5, 9 exists on the original function, then 9, 5 exists on the inverse function. So we can say that we flip the input and the output. That is 5, 9 maps to 9, 5. F of x maps to 9, 5. For the inverse function, I'll write that here. This is f of x, and this is f inverse of x. Okay. Now, something that hopefully we can see visually in our understanding of calculus, hopefully we see that here, let's say that this slope here, I'll draw a tangent line here. Let's say that this slope equals 8/3. Okay. Then the reciprocal, then the inverse function will also have a slope, and that slope, if we can see visually, it's going to be it's going to be a reciprocal of it. So that slope should be 3/8. Okay. So that's another thing we know about inverse functions. If you take any point and you kind of map it to its corresponding point for the inverse, the derivatives are reciprocals. So you can just say reciprocal derivatives. Okay, so you could say the derivative for this 5, 9 is 1 over the derivative at 9, 5. Okay, so the derivative at 5, 9 is 1 over the derivative at 9, 5. Okay, I know it's so reciprocal derivatives. Derivative at 5, 9 is equal to 1 over the derivative at 9, 5. All right, good. And so this gives us a few interesting things. And what I'd like to talk about now is how we can look at this algebraically. So here's what's happening. So there are a few things we'd like to consider algebraically, which we'll talk more about. Okay, algebraically, what's going on? Well, there are a couple things. The first, and this is, hopefully we can recall this from last year, the first thing we'd like to talk about is that f of f inverse of x, if you apply, start with this, f inverse of f of x, if you apply a function to x, take x, apply a function, and then apply the inverse of that function, the inverse by definition inverts everything. So you take some x, you apply a function, and then you invert everything, you undo it. And so you just arrive right back at x. Hopefully just that verbal explanation makes sense. This also gives us the corollary to that, which would be f of f inverse of x also equals x. Okay, so these two just go hand in hand. The inverse of the function is itself. The function of the inverse is just itself as well. And now let's say, on top of this, let's say that we have, suppose f of x and g of x are inverses of each other. Well, then this should yield the same result. It should yield f of g of x. If they're inverses of each other, then applying the g function and then applying the inverse of that function to it should arrive us back at x. And also g of f of x should also yield x. So this is a general understanding of what we know about inverse functions. Okay, and so we can work through a few examples here of what this could mean. And so here's one example that we have on the board, and I'll write it up algebraically. We'll just call this example 1. Let's say you're not given the graph, but you're given the algebra. Let's say you know that f of 5 equals 9, and you also know the derivative at 5 is 8/3. Now, using this information, you could solve for the inverse. I'll write this the proper way. This is going to look weird. The inverse function's derivative at 9 is going to be 3/8. So this is the idea. Okay, so if you have some function and you know what it maps to, and you know what the inverse of that is, then you know the reciprocal of that is going to be, or the derivative of that is going to be its reciprocal. Okay, so just kind of looking at this pattern, let's do a different one. Let's completely different example. This is from the graph here. This is not from the graph. This is a completely separate example. Let's say we have f of 3 equals 7, and we have f prime of 3 equals 2. Let's say, then I guess you would just say, all right, what's the derivative of the inverse function at 7? Well, it's just going to be 1 over that, 1/2. Okay, so a little bit of pattern recognition here. We'll go through one more. Example 3. Let's say that f of x and g of x are inverses. That's the first thing. Okay, and then let's say we say, oh, well, f of 4 equals 9. I'm not going to use 9, I'm going to use 10. F of 4 equals 10, and f prime of 4 equals negative 1/3. All right, then we can say, all right, well, if g is the inverse, then we know g prime, so that it's the inverse function. G is the inverse, so g prime, f inverse prime, g prime of 10 must equal the reciprocal of this negative value, which is negative 3. Okay. All right, so a few interesting results from that. And hopefully we can kind of see the logic here. All right, well, f of 4 maps to 10. We know the derivative at 4 is negative 1/3. So on the inverse function, if you look at 10, then its derivative should be the reciprocal of that. I'm going to say that sentence one more time. Okay. If you know on the original function f of 4 equals 10, and the derivative there is negative 1/3, okay, then on the inverse function, at the point 10, the derivative should be the reciprocal of this. Okay. And the point here, right, the point would be like the actual value of g. I mean, g of 10 equals 4 because f of 4 equals 10, right? So you flip them. And so at the point 10 comma 4, which exists on the inverse function, you have a derivative of negative 3. All right. I hope this is making sense so far. It's good stuff we're doing. All right, so then the question becomes, can we look at this a little more structurally in terms of the algebra? And we can. So that becomes our really immediate question, is what is happening algebraically? What is happening algebraically? All right. Well, let's look at. Let's start with this. We have f of. We know that f of g of x equals x. Okay. Oops. I'm sorry. I'm gonna put this on one side. Yeah. Oh yeah. We'll say that. Let's say that. Say f of x and g of x are inverses. Okay, we're going to divide this paper in half. Okay, so for this side, say f of x and and g of x are inverses. And for this other side, we're just going to use f of x and the inverse function in terms of f inverse of x. Okay, so say f of x and g of x are inverses. Then what we have is, well, we know that f of g of x is equal to x. Okay, and then on this side, we know that f of f inverse of x is x. Okay, because inverses undo each other. So hopefully that is good so far. All right, and so what we can do is we can say, all right, well, let's take the derivative. We're trying to find the derivative of stuff, right? So let's just take the derivative of this truth that we have. We'll take the derivative, and we can do both sides at the same time. Okay. So the derivative of f of g of x, this is chain rule, right? It's an interior function. So you're going to take the derivative of the outside function f, so f prime of what's in there, the elephant's in there, g of x, times g prime of x equals dx over dx, which is just 1. Okay, so I'll rewrite that. F prime of g of x times g prime of x equals 1. So on this side, what we have is f prime of f inverse of x times f inverse prime of x, taking the derivative of the inside, equals, I'm just going to write that here, as equals 1. Yeah, I know I'm correcting myself a little bit on this side. Okay, and so what can we do? If we're trying to solve for the derivative of the inverse, we would divide by f prime of f inverse of x. Okay, so we'll divide it out, and we write this as f inverse, the derivative of the inverse function is 1 over, like reciprocal, the derivative of the output of the inverse function. Okay, that is a really hard sentence. Okay, and I don't want you to worry about the sentence structure. I really want you to worry more about the pattern recognition and what's happening. But there's a mathematical justification for this that will help us really have a better understanding of what's going on. So if you know a bunch of information about f of x and you're wanting to find the derivative of the inverse function, g of x, here's what you do. Well, you want to find the derivative of g of x, which is g prime of x. So the same work as here. We would divide by f prime of g of x. So we'd have g prime of x equals 1 over f prime of g of x. Okay. Now this looks really strange, but let's just look at a few examples and see what it gives us. Let's look at, all right, let's look at another example here. We can call this example 4. All right, let's say we have, we can draw a graph. All right. So we have the function x cubed. X cubed looks roughly like this. Let's call this f of x. All right, now it's reflected about the line y equals x. Okay. And then you have the inverse function, which is, that. We'll call that g of x. And we'll say, g of x we know equals the cube root of x, because the inverse of x cubed is a cube root of x. Okay. All right. And so this gives us, so here's what we can do with this. Let's say we talk about the point 2, 8, which I'm going to put here. So today we're talking about this point, 2, 8. Now how can we use the information about this point to determine the derivative at 8, 2 of the inverse function? Okay, so here's what we can look at. So here's what we have. What's the derivative? What is g prime of 8? Well, from this, we know that g prime of 8 is going to be 1 over f prime of g of 8. All right, what's g of 8? Well, g of 8 is 2. So g prime of 8, the derivative at 8, is going to be, just down a little bit, g prime of 8 equals 1 over f prime of g of 8 is 2. Okay? And what's f prime of 2? Well, the derivative at 2 is this slope. And so what you can do is say, oh, this is our function, our derivative is 3x squared. Okay, so g prime of 8 is 1 over, plug 2 into here, 2 times 2, 4. I'll write it out, 3 times 2 squared. So g prime of 8 is 1 over 12. So that means the slope here is 1 over 12, and we were able to do it algebraically. Okay, the graph helped us understand, like, oh yeah, that slope's 12, okay, or 1/12, and which yields, we figured out f prime of 2 is 12, so this slope is 12. Okay, and so it's sometimes nice to see the graphical working together with the algebraic, but there are also ways to do these similar to the work we did over here without using the graphical without using a graph at all. And so that's what we'll do in the next example here. I'm just going to use this for working examples. Okay, so a few quick examples. We can call this example 5. All right, so example 5. Let's say you want to find the inverse derivative at 2 given the inverse of 2 is 4, the inverse, f inverse of 2 is 4, and the derivative at 4 is 7. Okay, now this feels really weird, okay, but let's see if we can look at it algebraically. So what we have is f inverse, the derivative of the inverse function at 2 is going to be, we'll look over here, 1 over f prime of f inverse of 2. Well, what's f inverse of 2? It's 4. So this is just 1 over f prime of 4. F inverse of 2 is 4. And what's f prime of 4? It's 7. Okay, so this is 1/7. And it should in a way make sense. If f inverse of 2 is 4, that means that f of 4 is 2. And if you apply the inverse to both sides, this goes away, it just becomes 4, and f inverse of 2 is 4. All right, so if f of 4 is 2, and the derivative at 4 is 7, so just follow this two-sentence logical piece here. If f of 4 is 2, and the derivative at 4 is 7, then for the inverse function at 2, the derivative should be 1/7, which is what we have. As the inverse function at 2, its derivative is 1/7. Okay. So there's a little bit of manipulation that goes on in these questions. And we'll do one final example here, and I'll erase this, and we'll just write underneath. Okay. Example 6. All right, so let's say that we have f of x equals x cubed plus 1. Okay, let's find the derivative of the inverse at 28. Oops. 28. That's all we know. Okay, good. So find the derivative of the inverse at 28. So f inverse prime of 28. Okay, so let's start with this algebraically, and then we can look at it graphically. So I'll draw the sketch of the graph here, or I'll draw there's the graph here. We're not going to look at that yet. We're going to look at the algebra. Okay. So looking at this algebraically, find f inverse of 28. The derivative of f inverse of 28. So looking at what we have over here on the right, okay, we know that the inverse function, f inverse prime of 28, is equal to 1 over f prime of f inverse of 28. Okay, now what is f inverse of 28? Well, f inverse of 28 means, so let's say what's f inverse of 28? F inverse of 28 is with an output, this input, so remember this? Flipping the input and the output. So if this is the input of the inverse function, it's the output of the regular function. So what we're really trying to say is, all right, you want to find f inverse of 28. What you're really doing is saying, all right, well, when is the original function equal to 28? So 28 equals x cubed plus 1. Subtract 1, cube root it, ends at x is 3. Okay, so what we have is that's 1 over f prime of 3. Well, what's f prime of 3? Well, let's take the derivative. F prime of x equals 3x squared. Plug 3 times 3 squared is 9. 9 times 3 is 18. It's going to be 1 over 18. Okay, this is probably the weirdest step. This comes back to our pre-calculus understanding of inverse functions, where if you take f inverse of 28, what you're doing is you're saying, all right, when is the original function's output 28? Okay, so say, oh, when is this thing, the output 28? So 28 equals x cubed plus 3, solve for x, they're doing it for that. All right, now algebraically, or graphically, what's going on? Graphically, we have the function x cubed plus 1, which looks like this. All right, that's f of x. Then you have f inverse of x, which is reflected. Let me turn this one up. All right. Reflected here. Yeah, okay. And let's say, here's what's going on. We're trying to find the inverse, the derivative at 28. So at 28, okay, what we need, and this is going to be drawn to not scale at all. This is 3, okay? Which means you have another point, 3 comma 28. All right, so if you have the point, if you're trying to find the derivative of the inverse function at 28, you can say, all right, well, it's 28 comma 3, which means for the original function at 3 comma 28, whatever that slope is, it's going to be 1 over that slope. And we found that that slope, cramping myself here, but that slope equals, we found it, it's 18, which means this slope is 1 over 18. All right, some stuff to chew on here. Some of this gets a little bit lost in the weeds of algebra, and that is why I am here for y'all in class. I'll see you then.